We started section 1.3 last time, and we were looking at the Cartesian Coordinate System. And let's see, I believe we're on number 5. Does that look right to you guys?
Yeah.
Awesome. Okay, so our goal when we're working with circles is to have them in this standard form. And the standard form looks something like this. So that x minus h squared plus y minus k squared equals r squared. And the reason I like that form, and you should like that form, is because it's really easy just looking at it to find the center and the radius. Okay? Now, over here, problem number 5 is actually a circle as well. But when you look at this form of the circle, it's not easy to see the radius and the center, right? And not only that, but it's not like a line where you can just, I'll solve it for y and I'll plug it into the calculator and I can find the pieces of information. It's not that easy because I've got a y and I've got a y squared. So solving it for y is also not just a super simple task here. So when we're working on a problem that looks like this, we're going to do something called completing the square. So what we're going to do is we're going to group all the terms that have x together, right next to all the terms that have y together, and then anything that's not got x and y is moving to the other side of the equation. So we're looking for something to sort of put it into this form, for the moment anyway. The x stuff, and then the y stuff. It's a technical math term, you know, right, stuff? Okay, yeah. Equals all of your just constants, your numbers on the other side. That's what we're looking to start with. And this one's actually already kind of like that, right? We have the pieces that have x in them, we have the pieces that have y in them, and then we have our numbers on the other side. So it's already sort of where I need things to be. All right, so we're going to take each piece at a time. That is the piece with the x's in it and the piece with the y's in it. So the piece with the x's in it, the linear term, linear is the term that just has x by itself right here. So this linear term, we're going to take the value at the beginning, the 8. Okay, so the key to completing the square is to take the linear term, divide it by 2, and square it. Okay, and I mean the number, the 8, not 8x, just 8. So if I take the negative 8, or the 8, doesn't even matter if you keep the negative or not. But if I take the negative 8 and I divide by 2, what do I get? 4. And if I square it, what do I get? 16. Everybody good with that? And so what we're going to do is we're going to rewrite the x squared and the negative 8x, and we're going to add 16 right beside it. But as with any equation, if I add 16 to the left-hand side of the equation, I have to balance it, right? An equation is a balance. So I have to add 16 to the right side of the equation. Is that okay so far? Okay, we're going to do the same thing with the y term. We look for the linear term here. So that's my 10 here. I take 10, or negative 10, either way. I divide by 2 and I get 5. And then I square it and I get 25. So again, I write down the y pieces, so the y squared, the negative 10y, and then I add 25 right next to the 10y. And if I add 25 to the left, I add 25 to the right. Is everybody good so far? Okay, let's just simplify the right-hand side. It's a bunch of numbers, add them together. I've got negative 5, positive 16, and positive 25. What does that combine to equal? 36 is right, yeah. Okay, very good. Now, it may not always be a perfect square like that, but this one actually was, so that's friendly. Now, the reason that we added these very specific values, right, the 16 and the 25, is because these will now factor perfectly as perfect squares. So, I mean, we can go through all the factoring like we did back in chapter P, but it's always going to factor because of what we just did as something squared. What will it be? Well,
X plus 4.
Close.
X minus 4.
Minus 4, yeah. So it'll always be the x squared term's square root, right? The 16's square root, and then the sign will match what's in the middle. So if we follow that pattern, what will the next piece become?
X plus 5.
Close. Y.
Oh, y,
And will it be plus or minus?
Is it minus?
It'll be minus. The sign will always match whatever's here in the middle on the linear term. Okay? So it's almost like you get one piece of each of these, right? So x squared, you get the x. The negative 8, you get the negative. The 16, you get a 4. You're getting a piece of each of the three terms. Now, this is cool because what happens next is it's really easy to see now, the radius and the center. On this one, it didn't ask us for the radius and the center. It does on the next one, just for good measure because you can see it. What is the center on this one?
4, 5.
Yep, 4, 5. And if you'll remember from last time, the signs switch, so you switch the signs perfectly. And then we have the radius. And what would the radius be on this one?
6.
Yeah, 6. It's the 36 and then the square root of it. All right, so it didn't ask for the center and the radius on this one. We just kind of went a step further. But on the next one, it does. It asks to find the center and the radius. And it gives us, again, an ugly kind of equation. At least it's not in standard form. So our goal, just like the last time, was to have all the x's grouped, all the y's grouped, and then all the constants on the other side. So again, this kind of starts out nice. I've already got the x's grouped. And the y's are already kind of attached beside each other anyway. But this negative 3/4, it needs to move to the other side. And it is a fraction, and I'm sorry about that, but you guys can deal with it. You know how to deal with fractions, right? You don't have to like them. You can still work with them. It's okay. All right, so let's take these and let's move that 3/4, x squared minus 3x. And I'm just going to leave a space next to that because I'm going to put a number in it here in a minute. And then I've got a y squared plus 2y, and I'm going to leave a space as well. And if I have the negative 3/4, I'll move it to positive 3/4. Yes, Chris?
When working that on the test, can we change that to a decimal?
The 3/4? If you want to. Yeah, as long as it's a terminating decimal, and 3/4 is. So 3/4, absolutely. 2/3, not going to work because you'd have to have a repeating decimal for it. But if it's a terminating decimal like this, you could. Yeah. There's actually something really nice on this problem that's going to happen, and you're going to want it, well, at least it's going to be nice sort of in fractional form. So bear with me for a minute, and you'll see what I mean about that too. All right, so same as last time. The key is taking these linear terms, dividing by 2, and squaring them. So I've got the negative 3, and I've got the 2. So let's start with negative 3. Negative 3 divided by 2 would be negative 3/2, which is ugly. And again, you could turn it into a decimal like Chris mentioned. It'd be okay. And what happens if you square negative 3/2? What's the top? 9. And the bottom is 4. So we have 9/4 right here. And I have to add 9/4 to the other side. That's what I was talking about, Chris. I do actually have common denominators on that one pretty nicely. And then the other piece is my 2. 2 divided by 2 is squared is still 1. So I add a 1 to both sides. Did I make? Yes?
Oh, no.
Are you good?
Yeah.
Joe and Jamie, we're all good?
No, I was showing.
Okay. All right. Are there any questions at this point? This one's trickier on the next step because of the fractions, and I do realize that. It would be tricky even with decimals on the next step too. But is everybody good so far? Okay. Portions of this are nice and simple, like the y portion. This is going to look like my last problem. I'm going to have a parenthesis. I'm going to have a y. I'm going to have the square root of the 1 at the end. That's 1. I'm going to have the sign of the 2 in the middle. That's positive squared. Looks just like the last problem. The other part with the fractions is a little less clear. So again, I'm going to have an x, and I'm going to have something squared. There is an addition sign between these. Occasionally I have students forget that there's positive between them. I do need addition between my 2 squared terms. It's a negative because the 3 is negative. That's just like before. And what I need is I need the square root of the 9/4. So in other words, what I need to know is what was it before I squared it? And it's over here, right? I kind of wrote it to the side on purpose so we could reference it later. It's 3/2. And that's the value that's going to go in that blank spot right there. And again, it's negative because there's a negative 3 in the middle. On the other side of the equation, what happens when I add 3/4 and 9/4? Just that part. What do you have? Right, I get 12/4, which is 3. You've already reduced it, yeah. So 12/4, which is 3, plus my 1 would be 4. And again, you've got a calculator if you want to use your calculator to verify and make sure you haven't made any addition errors. That's fine. I end up with 4 on the right-hand side. So, what's my center for this one?
3/2, -1.
Excellent. You remember to change the signs. Good job. 3/2, changed my sign. -1, changed my sign. So somebody else tell me what the radius then would be. 2, yeah. It's the square root of the 4 that's on the right-hand side. Very good. Any questions on that one? The fractions don't change the process, but they do make it a little bit more messy to work with. The last thing in this section that we're going to take a look at is just a little bit about lines. In particular, we're going to look at the standard form of the line first. The standard form of the line is written as ax plus by equals c. And there are some considerations for it to be considered standard form. A and b are not both 0. And I don't know why it's not written on here, but let me go ahead and write it in. A, B, and C. Actually, let me start. Yeah, we'll do this. A and C are whole numbers. And A is positive. Those are also a couple of conditions that show up for standard form. Okay. So the equation that we're given right here is in standard form. 5x minus 2y equals 10. So one way to do what the problem asks, which is to graph it, would be to solve it for y. You can even verify it with your calculator, and you can do all of that. But it's actually leading you down a slightly different path that's actually really nice if you're aware of it. It's asking you to do it with intercepts. So intercepts means what happens when you have the x equal to 0 or the y equal to 0. So if you think about the ordered pairs, we're going to find the ordered pair when x is 0 and the ordered pair when y is 0. Because that's going to be 2 points on my line, and all I really need to graph a line is 2 points. And it's always nice to let things be 0, right? I mean, lots of stuff just disappears when zeros show up. So when I'm working with this one, if x is 0, the 5 times 0 cancels out, right? So I'm left with 2y equals 10. And what's y? -5. So this is one of my intercepts, 0, -5. And then the other one, so we'll start out with whatever it was before, 5x minus 2y equals 10. And we're going to let y equal 0. So this time the 2 times 0 cancels out. So I'm left with 5x equals 10. And what would x be? 2. Yeah. So there's nothing super special about intercepts except that they're typically easier to find than just random points because zeros cancel things out very quickly. So over on my graph, those are the 2 points that I would plot. 0, -5. So 0 means I don't go left or right, anything, but I go down 5. So here's the first point. And then the second point is x is equal to 2 and y is equal to 0, which should be roughly here. So these are my 2 points that I would plot. And then I would connect them with the line. Okay. Maybe it's not the way that you're used to graphing. That's okay. It's another way to graph, though, that works pretty well. And finding intercepts is usually a pretty nice thing to find. So we're going to try the same thing with problem number 8. It's messier because I have fractions, but it's okay because lots of things are going to become 0, right? So some of those fractions are canceling out sort of as we go. So the first one we'll do is we'll let x equal to 0. So that's 1/2 times 0 plus 1/3 y equals 600. So this piece is gone. If I have 1/3 y equals 600, what can I do to move the 1/3? What operation? Either multiplication or division. Multiplication, what would I multiply by? 3. I kind of like multiplication here. In my mind, it's a lot easier to think about 600 times 3 than 600 divided by 1/3. So what is 600 times 3? Yeah, 1800, right. And then we'll do the same thing with the other one. So 1/2 x plus 1/3 y equals 600. And we're going to let y equal to 0. So I have 1/2 x plus 1/3 times 0 equals 600. Or 1/2 x equals 600. And then what would I do with my 1/2? Multiply by 2. Right. So what would x equal? 600 times 2? 1200. Thank you. So over here, I have 1200. Now, when you're working inside of my math lab, they'll give you a grid that makes sense to work with this on and so forth. Obviously, I'm not going to hash mark out 1800 or 1200 units. That's unrealistic. But I can mark them out so that they're fairly evenly distributed. So like this is 600, 1200, 1800. And then what's the other one? It's on the positive as well. So 600, 1200, 1800. So on the y-axis, I'm supposed to be at 0, 1800. Which should be here, and I'll label it. And on the x-axis, I'm at 1200, right here, like so. And then I'm going to connect my dots. All right, is that good? Now, there are two very special forms of lines that we're going to end this lesson with. In particular, they're horizontal lines and vertical lines. There's a wonderful acronym. It's not super common, so you probably haven't heard this acronym before, but it was introduced to me a number of years ago, and I really like it. The acronym is HOIVUX. And let me show you what it stands for. We're working with horizontal and vertical lines, so that's obviously the H and the V. Okay, so this is horizontal. The O is actually a 0, and it's talking about the slope. It's 0 slope. And the Y tells you that the equation is Y equals some number. No variable X, just Y. And then if you do the VUX part of it, let me shift it over just a little bit. You're doing the same thing. We've got vertical. It's a vertical line. Any idea what U might stand for? Undefined. Yeah, it's an undefined slope. And then the X at the end stands for that we have an equation of X equals a number. So if acronyms are your thing, this is a nice one. I really like it, actually. And what it does is it allows us to remember quickly whether I've got a vertical line or a horizontal line without having to sort of reason through it every time. So when we're dealing with the last two examples, it's kind of combined, but part A says that we're going to graph x equals -3. Well, x equals is in the second part of this, right? X equals is a vertical line. So over here on my graph, I've got a vertical line at x equals -3. So here's -3. And the line that it's referencing is this one. So this is the line. I keep drawing random lines today. X equals -3. And then the part B, the y equals, okay, HOY, H-O-Y, tells me I have a horizontal line. So I have a horizontal line at a y height of 2. So my horizontal line would look something like, we'll do this color, see if it shows up. Is that all right? Yeah, it's not too bad. It's not straight, but the color's not bad. All right, so this is at a height of y equal 2. So this equation would be the equation y equal to 2. Okay? And it's not the only way to remember, obviously, the horizontal and vertical lines and which one goes with what. You could reason it out every time for sure. If you wanted to think about, for example, the y equals 2, every point along this blue line has a height of 2, right? At every location. So you could think through it that way as well. Any questions?